Hello and welcome to Starfish Maths. My name's Sarah and today I'm looking at arithmetic sequences. This is part of a mini-series on series, so it might help you to look at my video on recurrence relations first. As ever, please do grab a pen and paper and do the work yourself alongside pausing the video and rewinding as you need. Let me know how you get on in the comments below. I love to hear from you, and do get in touch by email starfishmaths@gmail.com or Instagram if you'd like any information about small group masterclasses or individual tuition. I hope this is helpful. If you're ready, let's get started. So here we have a very basic arithmetic progression or sequence, and that just means we're starting with a number and adding the same thing every time, which you can see is 5 here. Keep adding 5. When we talk about arithmetic sequences, we use some specific language, and that is we take the first term and call it A. So here that's 4, and then we're adding a number every time. Here that's 5, but in general terms we say we're adding D, and D is called the common difference. So here A is 4 and D is 5. The next term along we'll be starting with that first term and adding 2 lots of that difference, so adding 2D. The next term along again we'll be starting with that first number and adding 3 lots of the difference, so adding 3 lots of 5, and so on. Now we call the first term U1 and the second term U2 and so on. So in general we tend to use the letter N for whatever number of the sequence we're on. So here N would be 2, it's the second term of the sequence, and notice here that we're just adding 1D, and for the third term we're adding 2D, and so on. So we're always adding 1 less of those differences than the term that we're on. So a general expression for any term of the sequence can be given by UN, and that's what we're going to call it. N is any position in the sequence, so the fifth term N is 5. So a general term UN, we start with the first term and we add 1 less of whatever position we're in. So 1 less than N, lots of D. So I hope that makes sense. You of course can learn that off by heart, or maybe that's intuitive and you can just generate that yourself. But just let's walk through one other term just to make that really clear. Say we want to find the 7th term in this sequence. So if we want the 7th term, we're looking for U7. So we'll be starting with A. We know that A is 4, starting number, and because N is 7, we'll put that in as Rn, and we're multiplying by difference. The difference in this sequence, as we said, was 5, so we're timesing by 5. In your head or using the calculator, that gives us 34. And you can check that by just adding 5 each time until you get to the 7th one. Hopefully you get 34. So for arithmetic sequences, you do need to know this general term, and you also need to know how to add up a certain number of terms in the sequence. So that gives you what's called an arithmetic series when you're adding all of them. So say you want to find the sum of the first 5 terms of this sequence. We'll look at how to do that now. I'm going to show you how to get the formula for that. So to show you how to generate a formula for the sum of the first few terms of an arithmetic sequence, I want to tell you a story about a mathematician called Gauss. I don't know if you've heard of him, but the story goes that when this mathematician was at school, he kept going through all his schoolwork very, very quickly. So to keep him occupied, his teacher gave him a task. She thought it would keep him occupied for a long time. She asked him to add up the first 100 numbers, all the numbers 1 to 100, and he did it really quickly because he didn't just go 1 plus 2 plus 3 plus 4. He used a very clever method, which I'm going to show you now. So his arithmetic sequence was the most basic one. He started with the number 1, so his A was 1, and his common difference was 1, so he just went 1, 2, 3, and so on. I'll go up to, I'm not going to write them all out, but I'll go up to 99 and 100. And then what he did was he said, okay, I'll flip the numbers round and write them again underneath. So he put 100 underneath the 1, 99 under the 2, and so on, down to 2 and 1. He then added these up. He noticed that 100 plus 1 is 101. 99 plus 2 is also 101. 3 plus 98 is also 101, all the way to 101 and 101. So to add all these up, it's the same number every time, and there are 100 of them. So he said there's going to be 100 lots of 101, but that gives me the sum twice, because I've written out the numbers twice. So I also need to halve that total, and that gives you the sum. So 101 times 100 is 101 with a couple of zeros after, divided by 2, and that gives 5050. Isn't that clever? So in a very similar way, we can work out the sum of any arithmetic sequence using general letters. Let's have a go at that. So we're going to use the same method as Gauss. We're going to list our numbers, and we're staying general here. So the first term is A, and the second term is A plus D, and so on. The last term will be A plus, we don't know how many of them there are, but we'll call it N. So N minus 1D, that's our general expression for a term. And then it's just the same as Gauss, we'll flip them round and write them again underneath. Don't think I've got enough space, but I'll write it here. A plus N minus 1D. I won't write the next one, but I'll write under here A. And then adding those up. So remember, he added these up and found they were the same every single time. So A plus that will give us 2A plus N minus 1D, and you'll get that every time. So then we've got 2A plus N minus 1D every time, and we've got N lots of them. So N lots of 2A plus N minus 1D. And remember, that gives you the sum, but it gives you it twice. So we need to halve that. So you can put it all over 2, but generally people write it at the beginning here, so they put the N over a 2. And that's it. That's the formula for the sum of an arithmetic series, and we'll call that Sn. So the general term was Un, this is Sn for a sum. Again, you can learn that off by heart, but it's also good to be able to derive it yourself. I think you actually need to know the derivation, the proof, but in any case it's just good to be able to derive something so you know where it comes from. And a quick example of using this to find a sum. We'll go back to our original arithmetic sequence. So the starting number A is 4 and the difference is 5. So just to check that this formula really does work, we can find the sum of the first 4 numbers, because we know what the first 4 numbers are, so we can actually add those up using a calculator, and check it's the same when we use this. So N here is 4. You can write these out if that helps you, otherwise you can substitute them straight into the formula. So 2 lots of 4, and then 4 minus 1 multiplied by 5. And I make that out to be 46, which I get is the same as just adding up these numbers here. Great, hope that's making some sense. Let's take a look at some exam style questions now. Okay, so here we've got a question which was written in words, but I've written it in shorthand. We were told that the second term of a sequence is 8, the fourth term is 20, and we're asked to find the sum of the first 10 terms. So we've got our expressions for general term and sum, and we can use them to solve this question. So straight away we can set up equations with these pieces of information. So 8 is our second term. So using the general expression, we've got A plus N minus 1D. N here is 2, so N minus 1, 2 minus 1 is just 1, so that will just be 1 lot of D. Have a go at doing the same for the fourth. We've got 20 is A plus, and this time it will be 3D. N minus 1 there is 3. So we've got 2 equations. I'm sure you're able to solve those simultaneously. You can set them both equal to a and then make them equal to each other, or you could just take one away from the other. I think I'm going to do that, so I'm going to label them equation 1 and equation 2, and I'm going to do equation 2 take away equation 1. And that gets me 20 minus 8 will be 12, a minus a vanishes, and 3d minus 1d is 2d. So that tells me that d is 6. And then we can put that back into one of these equations. So substituting into equation 1, we've got that 8 is a plus 6, so a must be 2. Checking those back in there, 2 plus 3 times 6 will give us 20, so that's right. So I'm going to write these up at the top so we can carry on and find the sum of the first 10 terms. Do have a go at this yourself. So finding the first 10 terms, we're using that formula for the sum, so hopefully you've written that down or you know it. It's n over 2, here n is 10, and then 2 lots of a is 2, plus n minus 1 times your d, which is 6. And on the calculator I find that that is 290. Well done if you got that. If not, do rewind and have another go. Okay, here we have a second question. I've actually written this one out by hand, just so you can see the kind of language we're using. So it's telling us the sum of the first 10 terms is 400, and then the sum of the next 10 terms. So that means the sum of the 11th up to the 20th term is 1,000. So we're asked to find the first term and the common difference, a and d. We can do the same as the last question by setting up two equations and solving them simultaneously. But the two equations we're going to set up this time are by using the sum rather than the general expression. So we want the sum of the first 10 terms, so do have a go at setting that one up. So we've got the first 10 terms is 400. And that would be 10 over 2 using that expression again. We don't know a, and 10 minus 1 is 9, I'll just write 9 this time, times d. 10 over 2 is 5, I'm just going to change that there. And just to simplify this even more, we can divide that 5 onto that side to give us 80. So there's our first equation using that piece of information. Now let's look at the next piece of information. Now the easiest way to deal with this is probably to do a formula for the sum of the first 20 terms. So we know the first 10 terms add up to 400, and then the next 10 add up to 1,000. So the whole first 20 terms add up to 1,400. So we're going to do the expression here for s of 20. Have a go. That's 20 over 2 at the front, which I've simplified, and again we can divide that down onto that side. So here we've got our two equations and we need to solve them simultaneously. So do have a go at doing that in whatever way you like. So taking the 54 off the 80 to give 26 and dividing by 2, I get that a is 13. And of course checking those values back in the second equation, and that does give 140. Fab! Let's look at one more question. Okay, the last question I want to look at today is joining this up with the recurrence relations stuff. So I've made another video on that if you need to take a look, but these topics are very similar and can intersect. So this is written as a recurrence relation here, and this is saying that the first term is 7, and then a term is given by the previous term plus 4. So this is an arithmetic sequence. It's just written as a recurrence relation to begin with, to give us the information. So we're asked to find the 17th term. So the best thing to do is to pick it apart as an arithmetic sequence, treat it like that, and use that expression for the 17th term. So it might help if you just generate some numbers. The first term is 7, the second term will be the first term plus 4, so that's 11, and the third term will be that 11 plus 4 again, which is 15. We don't need to generate many at all because we can see that the first term is 7 and the common difference here is 4. You can do that, or you might be able to just tell looking at that those are what those numbers mean. So we can now put those numbers into our expression and find the 17th term. Do have a go. I make that to be 71. Great, there is another part to this question, I'll show you now. Okay, slightly more juicy second half to the question. I wanted to show you this just to show you the language that can be used here. Again, in the recurrence relation video I made, I talked through this notation here. Sigma, this is the sum from 1 up to 35 of UN, so all the terms from 1 up to 35. So that's just another way of saying S35. It's just another way you can write that. But it's written like that to use this here, so this means the n of 36 up to 50, so this is the sum of the 36ths up to the 50th term. So, to put that into our arithmetic sequence language, this here is the sum of the first 50 terms without the sum of the 35. So it's actually the sum of the first 50 minus the sum of the first 35. Does that make sense? So if you take off the first 35, then you're left with the 36th up to the 50th terms. We're wanting to show this, so we need to find the sum of the first 35. We also need to find the sum of the first 50. So have a go at doing that. We already know our A and D. I'm putting that into the expression. Okay, I get 2625 for that first one. And then we need the sum of the first 50. Do have a go. I get 5250. So you might notice, you might spot that that's double that one. So this is going to work. S of 50 minus the S of 35 will be 5250 minus 2625, which gives us 2625. So that's the same as the S of 35. I've totally run out of space, but hopefully you can see that works. So we've shown that this is 2625 and that is also 2625. So we've done it. Brilliant! Well, I hope that's making sense and I hope that was helpful and shed some light onto the sorts of things you can do with arithmetic sequences. Keep practicing a variety of questions on that and have fun. Thank you so much for watching.